paper. This is an interesting paper because it's actually from 2020, but it is from a Chinese group, and they're doing this work with Braitenberg Vehicles. And the interesting thing about this is that they're basing a Braitenberg vehicle on memristic neuromorphic circuits. So, we think about the Braitenberg vehicle as a toy model and how it's a very simple sort of connection between the sensor and effector, or maybe the light sensors or something like that, in a wheel. So if we have like two light sensors on the front of a vehicle and two wheels on the back, there's a mapping between that sensor and effector. It could be like a cross connection. It could be a ipsilateral connection. It could be, something more complex. And so that's the way we almost think about it as a very simple connectome. And so, but in this paper, what they're doing is they are trying to use a simple memristic neuromorphic circuit because they want to apply this to engineering applications. So again, we went back to Braitenberg's work on neuroanatomy. This was this last summer. There's several features that I did on this where we went through his thinking from like being a neuroanatomist in insect physiology to thinking about how you would simulate a nervous system. And so it was like a progression from his work in the 50s and 60s to this, this artificial sort of biocybernetic approach that he took leading up to his 1984 book and beyond. So this is kind of, where he was coming from. In this case, what they're trying to do is they're trying to develop this memrister that can do basically the same thing, that is, respond to stimuli adaptively, generate behaviors, and provide this mapping from sensor to effector. So let's start with the abstract. The Braitenberg vehicle was a simple conceptual model to characterize the response behaviors of animals or insects under a stimulus. It is widely used to develop autonomous vehicles able to adapt to the varying environments that you see in maybe the world. I mean, in Braitenberg vehicles are very stereotype sorts of stimuli, but you can have all sorts of complex stimuli. And that, of course, would result in even more complex behaviors than we see in Braitenberg's vehicles, as demonstrated in the book. Considerable effort has been devoted to building neuromorphic processors with the software in the vehicles. However, there has been no demonstration of Braitenberg vehicles with neuromorphic hardware so far. So people have actually tried to use or to build neuromorphic processors with software, but they haven't demonstrated it with hardware. So herein, a Braitenberg vehicle with simple memristive neuromorphic circuits is built for the first time. This vehicle exhibits adaptive behaviors in the supervised learning process and is eventually trained to conduct the task of tracking paths. So basically, it's trying to train they're trying to train the vehicles to follow or do path following, basically following a stimulus, following that gradient outward, and building a path. Moreover, the memristic circuit in the vehicle demonstrates a very short response latency, and they estimate that at about 56 nanoseconds to input sensory information. Herein, an alternative promising solution is to build self-adaptive robots and pave the way for realization of autonomous robots based on memristive neuromorphic circuits. The introduction is that they kind of go over they review self-adaptive behaviors, which are of crucial importance in varying environments, and it helps animals or insects avoid obstacles. And so they talk about the Braitenberg vehicle being this thought experiment and this toy model, and then they kind of describe that. In spite of much success in achieving autonomous robots based on this vehicle model, the processors of the smart robots are still based on von Neumann architectures. What they mean, I guess, is when people implement Braitenberg vehicles as robots, they generally use a von Neumann architecture to do so. So usually if you have a Braitenberg a robot that's a Braitenberg vehicle instead of a computer simulation, you're using a von Neumann architecture to simulate this sensor effector mapping. So this is limiting, of course, in the sense that it's, maybe not biologically inspired, and it just behaves maybe like any other robot at some level. So what's the point of using the Braitenberg vehicle? So far, the well-known Braitenberg vehicle model has never been implemented on neuromorphic hardware. And so neuromorphic architectures allow for the implementation of dynamic neural control through physical computation. On this architecture, information is transmitted and processed in the analog domain, enabling low power consumption and low latency. Previously, works have shown that various neural networks can be mapped onto memristive crossbar arrays for self-adaptive learning. For the memristive architecture, the non-volatile property and processing in memory improve the energy efficiency, which arises from the ions migration. The advantage of memristive architectures is not limited to energy efficiency. Avoiding the conversion between analog and digital considerably reduces time delay in information transmission and processing. So there's this analog aspect of the stimulus, and it has to convert in the von Neumann architecture. It has to convert it to a digital signal and then convert it back out to an analog behavior. In the memristive case, you don't have that conversion, so it reduces the time delay. This is why they cited the very short response latency in the abstract, because it's basically not doing that step of converting the signal. Considering the aforementioned advantages, it is interesting to build the Braitenberg vehicle with memristive neuromorphic circuits. And so here for the first time, they build a Braitenberg vehicle based on a very simple memristive neuromorphic circuit, which is 2 grayscale sensors, a memristive neuromorphic circuit in the middle, and then motors, which drive the wheels. With a supervised learning rule, the vehicle can be trained to track a path. Furthermore, a very short response latency is achievable for the memristic circuit of the vehicle. And so this is where they're kind of very into the technical aspects of a memristive circuit. But this, of course, we'll go through their figures, and that gives a little bit more context here. So this is an example, of course, of an insect nervous system where you have the compound eyes, you have the brain, you have the locomotor system, and there's basically things are coming into the eyes, being processed by the nervous system, and then being mapped out as movements in the limbs. So you can see that here. And so they're behaving, and that was, of course, the inspiration for Braitenberg vehicles, which you see an example of here. And so here they have, so in A, they have, of course, the ant engaging in obstacle avoidance. So this ant is moving around the stalk here, and it's doing so through this system that I just described. So it's doing this path following. It's able to develop an adaptive path through an cluttered environment. Image B is an electron microscopy image of a 1x16 memristor crossbar array. So that's here. So this is the hardware that they're using. C is continuous conductance tuning performance on these memristers under the stimulus of electric pulse. And this is the chemistry here, TA205. So this is the sort of the deposition of the layers, the metal layer, 80 nanometers of TA205, which is 10 nanometers, another metal layer, and then the substrate. And then we have in D, continuous, that's the D. Actually, the schematic array was here, and then this is the performance in terms of conductance in D. So they're, given the pulse number, what is the conductance? And then E is model a Braitenberg vehicle, including grayscale sensors, memristive neural processors, and steering control systems. So this is the setup here is diagram. So the grayscale sensors are here at the bottom. You have the steering control. You have the bio-inspired processor, and it's going forward in this direction. Grayscale sensors are kind of back here, and it's picking up the information and it's moving and following a path. F is the top view of this assembled Braitenberg vehicle. So here's the vehicle here. The sensors are down here. The wheels are here. This is the processor. The steering control is down here. This is a top view. And then G, demonstration of obstacle avoidance behavior that the vehicle exhibits. So if you can see here and compare with what we saw with the ants, we have this cluttered environment where you have obstacles, and the vehicle is able to get around those obstacles, much like we see with this ant avoiding this stalk. Okay, so they go through the training of the Braitenberg vehicle for path tracking. They say that the locomotion mechanism of the Braitenberg vehicle is determined by neuron interconnections. By changing the connections, the Braitenberg vehicle exhibits different and complex behaviors under the same stimulus. Therefore, the capability of learning and adapting to the varying environment is crucial for the practical application of this. So in figure 2, they show a flowchart to illustrate how a supervised learning process is performed in the memristive neuromorphic circuits. The weight in the artificial neural network would be updated according to the punishment or reward feedback instructed by the supervisor, which is based on different response behaviors of the vehicle to input signals. After a few iterations of the feedback loop, a new mapping relationship between the input signals and the output signals will be established, which indicates that the vehicle acquires a new skill. So they have this whole training regimen where there's the supervisor, and it's giving this sort of reinforcement learning approach to stimuli and to encountering stimuli. So when you encounter a stimuli, the supervisor looks at the weights, it gives feedback. The feedback is either positive or negative. The negative is punishment, the positive is reward, and then this allows us to have these different mapping relationships over time that change the behavior so it can follow this path. Traditionally, weight update process of the memristive neural network is controlled by the software in a digital controller, such as a personal computer or a microcontroller. So we have this, this weight update process. It's going on kind of separately from the navigation, and it's just kind of giving feedback. Note that we have implemented neuromorphic neural networks in the vehicles using memristive crossbar arrays. On this neuromorphic hardware, we update the weights in the artificial neural network through a simplified method without using the traditional digital controller. So they describe this process in a von Neumann architecture, but then they describe it in the neuromorphic architecture. So they go through the weights here and kind of how this is done, all the methods here. So this is figure 2. So A is a flow chart of this process. We go from the environment. Information from the environment is captured by the sensors. The sensors then pass this to the bio-inspired processor, where you have the simplified neural network where you have afferent neurons, this memristive arrays for synapses, which just map the afferent neurons to efferent neurons. The afferent neurons take in information from the sensors. The efferent neurons are the output layer that map that to the motor control of the vehicle. And so the WIJ matrix is just the mapping between those. And those weights then of those connections are sort of given feedback by the supervisor. When the weights are positive, they give positive feedback. When they're negative, they give negative feedback. And negative means basically you're headed towards an obstacle. Positive means you're on a path that avoids an obstacle. And so then that leads to motor control. Now figure 2B is the detailed circuit diagram of the Braitenberg vehicle. So this just describes this as a circuit. So we have grayscale sensors, 2 grayscale sensors. We have the battery, a driving engine, and the pulse generator. The grayscale sensor is mapped to this internal supervisor. So this is where you have this sort of much more coarse grained map that we can follow that basically gives the feedback signal. So it's either positive or negative. That's why we use this 2-bit grayscale sensor. And then we have the pulse generator, which generates information from the environment. This goes into this network. The supervisor evaluates the network and provides feedback. We have the reward feedback and the punishment feedback. So we have, that's a binary value that goes into this network. The device selector is learning mode 1 and working mode 0. So it's either going without learning or it's actively learning. And you can switch between the two. And then there's the steering engine and a differential amplifier. So once this network is supervised and given the proper feedback, then it goes through this differential amplifier. This oscillator is added to the generator, and then this is giving the steering engine, which gives you the motor output. Okay, so that's basically how that's structured. This is figure 3. This is a demonstration of learning process again. This is where this graph in A is where we go over time, and we have the normalized weights of each connection, 1 positive, 1 negative, 2 positive, 2 negative, and this just shows the normalized weight of that. And this is, I guess, normalized by, I don't know, from 1 to 0, I guess, or 0 to 1. And then, so our iterations here, we see that over time, we get these weighted, or these normalized weights. So the positive is positive feedback, the negative is negative feedback. And so we have these graphs here which show over time that it's learning from the environment. And then we see the behavior of the vehicle. So in iteration 0, the vehicle travels in a straight line, even though it's supposed to make this curve. It doesn't make the curve successfully. In iteration 24, it's learning how to make a curve, but it doesn't make a curve successfully, or at least 2 curves successfully. It kind of makes a curve and then goes off on a tangent. And then finally, by iteration 37, it is able to learn this course, where it actually needs to make 5 or 6 curves, I think, to make it all the way around the circuit. So to recap, iteration 0, it learns nothing. It's just operating on input-output. In iteration 24, it's partially learned how to make curves, how to make turns, but it only knows how to make the 1, or actually 2 turns, but it only knows how to make that curve, and that's it. And then by the iteration 37, which isn't that much time from iteration 24, it manages to leverage that knowledge of curves, or that ability to curve, into making multiple curves to follow the path. And so then this is just the gray value at the left sensor, gray value at the right sensor. So the differential learning between left and right. And you see that there's this difference over time where you get this iteration 0, it's basically random. Iteration 24, it's kind of figuring out a gradient. And then in iteration 37, there's this sharper gradient, which allows it to do this sort of behavior. And so then, yeah, they kind of give this overview of the memristive circuit and the different inputs and out, or the different input values and that sort of thing. Remember, this is an analog system, not a digital system. And then, of course, they show the difference between the memristive neuromorphic circuit and a digital von Neumann circuit. The analog domain is where the environment is. And when you use a von Neumann circuit, you need to do some sort of analog to digital conversion, and then process things and then go digital to analog for the response behavior. But in a neuromorphic circuit, you'd use parallel processing, not serial processing, and you keep things in the analog domain. So there are 2 benefits to that.